Yeah. Okay, so hello, can everyone hear me? Okay. So hello everyone. I will talk about complexity of interaction. I will explain what interaction means here. And I start with some possible motivation for this work. So one question, is it?
Speak louder.
Okay. So one possible motivation for this work would be to run automatically functional programs in a parallel setting. So this is an example of a simple program written in a functional programming language without any threads or network invocation. And it's possible to run it in parallel if you notice that both arguments here, I don't consider effects. So I mean, so to say, pure lambda calculus. So both arguments can be run in parallel. There's no issue with that. And so we may want to automatize the parallelization of this code. So a question that arises naturally when you want to do that is how to estimate the resource needs of the different parts of the program. So by resource needs, I mean here time or space. So what may answer this problem is the topic of this talk. So we will provide some kind of formal complexity specifications using the type system. So that's the usual type for merge sort. So it takes a list comparison function and returns a list. What we will do is to first annotate these normal types with annotations. There are formal annotations like this. Here we use the sizes of the objects. So we specify that when we use merge sorts with a list of size n, we will output a list that has the same size. And we also will annotate how many function calls we need depending on this formal annotation. On top of that, we will define resources, time and space resources that will be parameterized by these formal annotations. So here I have only one, and there could be many. And this can depend on all these formal annotation that you add in your types. So the outline of the talk will be a presentation of the computation model we use and the associated cost model. Then we will do some sequential complexity analysis using size types, which is a known notion. Then we will show how we can do similar things for parallel complexity, and we will introduce scheduled types. And I will talk a little bit about how we can deal with higher order. So interaction nets, they were presented for the first time in Popol 25 years ago by Yves Lafont. It's a very simple computation model, and we use it well, because of the simplicity and because it can be used to model sequential and parallel reductions. So it's a graph language with nodes that look like that, and all reduction rules have this shape. So they are constituted, redexes are two cells connected by their principal ports, and this has nice properties. So today, as examples, I will use natural numbers. So you have constructors and some functional natural numbers, lists, so list constructors and some operations. And that's the kind of reduction rules you want to use to do functional programming with interaction nets. So just to give you a taste of what reduction looks like, oh, I'm sorry. That's the camel equivalent of what's written here. So we will perform the list.map on a list that contains zeros, and we'll just add one constructor successor to all of the elements. So initially, I have only one redex, which is here. So I don't have much choice. I can only fire this one. And here you have a choice. You can choose to do parallel reduction or sequential reduction. With sequential reduction, I would have to choose one redex, fire it, then choose another one, and do this sequentially. The parallel reduction I consider here is every time a redex appears, it is fired in the next step, so everything at once. So that's what I'm showing here. There will be a couple of parallel steps until we reach, finally, some normal form. OK, so that's the kind of parallel model I will use and study for complexity analysis. So it's a nice model because it's realistic. If you try to implement this on your computer, you will notice that you can perform the firing of one redex with bounded resources. So that's really nice. And you have additional properties such as those. Sequential reduction satisfies automatically the diamond property. And parallel reduction is the one that you can hope to implement with maybe GPUs, electronic chips, or by distributing the computation of the network. It is strictly deterministic in the ideal case. So the ideal case is every redex can be fired as soon as it appears. Resource cost will be very simple. For time, we consider the number of steps or some little refinement. We can attribute different durations for different reduction rules and sum these durations. For space, typically what you want is count the number of nodes you have in your net. And you can also refine it to node weights and make a sum of all the weights of the nodes of your net. So we will use typing. That's what it looks like in interaction nets. It's just the same as for lambda calculus, for example. You just add some annotation on all input and outputs of your terms. You have the usual type unification. So when you link cells together, for example, if you link a successor as an element of a list constructor, you will, of course, obtain as output type a list of natural numbers. And sometimes unification is not possible, and you are not allowed to build a net that connects, for example, a natural number to something that expects a list. OK, so what makes typing work is that it is always required that reduction rules preserve the types in the interface. So here, as you can see, the interface hasn't changed, and this should be the case for all reduction rules. OK, so that's typing in interaction nets. We will add, to perform complexity analysis, sizes. So it's very simple idea. You just can define some type nat n that stands for all natural numbers that are bounded by n. This is the typing schemes you need to use for that. You will also need to have some subtyping rules, subtyping, let's say, cast operators. I'm not giving the details, but it's quite easy to deal with that. And now, if you choose to add size notation to your addition operation, or maybe your concatenation operation on lists, to ensure that you have provided a correct size analysis, you just need to check that the reduction rules still preserve the interface. OK, so now that we have added size annotations in our types, we can perform, we can find a way to obtain complexity of nets. So for that, you use this theorem in the case of sequential time. So this theorem says that a net n, every reduction of a net n, the duration it takes will be bounded by a sum of potentials that are associated to the nodes in the net. So it assumes that you already have some library of cells annotated with potentials. And the trick that makes this theorem usable and useful is that the potentials are associated to type nodes. So they are parameterized in the annotations that we already mentioned just before. So these potentials have to satisfy some properties. So namely, for every reduction rule, the sum of the potential in the left-hand side has to be bigger than the sum of the potential in the right-hand side, modulo some added duration. So you do this for your library, and if you do this for your library, if you find appropriate potentials, you are able to deduce complexities of all the nets you build with this library. And before you compute this sum, you have to type the net. There's a very similar theorem for space. It looks exactly the same, except that instead of depending on the duration of the rule, it depends on the weights you have attributed to nodes. And this is an example of what a library could look like for integers or natural numbers. So we had to come up with the right complexity annotations, but now if you have those, you can check very easily that they satisfy the hypothesis, and you have a way to know what will be the complexity, the resources you need to build to run any net built with these nodes. So now I'm coming to parallel reduction. This was for sequential reduction. For parallel reduction, sizes of objects are not enough. You need to add some timing information in the types, and we'll introduce scheduled types. And scheduled types are types that you may obtain using this delay operator. So the idea is quite simple. If I delay A by T, it's the type of object that will become an A after duration T. And using this delay operator, you can, with some simple recursive type definition, define, for example, it's just an example, natural numbers that are computed with space D. So it means that the first constructor is available now, and the next constructor will be available after D units of time, and so on. That's an example, and that's how you can define it. You can also combine these timing annotations with size annotations. It's useful in the general case. And for these types, you need to change a little bit the rules of the game. Now the interface should not be preserved, but you should have some delay consumption. So if you attribute duration D to your reduction rule, you must make sure that all outputs have delays, and that these delays are consumed by firing the rule. For inputs, it's a bit more flexible. You should just make sure that, you can reduce the delay by any amount between 0 and the rule's duration. You are also allowed to be able to type your rules to delay computation. If this is a valid typing scheme for your cell, you are allowed to use it delayed. So you delay all the types. So if the inputs are available only later, you can run your computation later, and you will obtain outputs with just this delay. So that's fine. We obtain some property for all normal algebraic data types. That is subtyping. If you have an object that is immediately available, you can cast it to something that is usable later. That's not a problem. So these are examples of specification we can add to add or to multiplication. These are two different implementations, and so you should read them like this. Addition asks for its first argument now. There's no delay around this natural number. It will ask for its second argument here after delay 1, bracket without exponent is delay 1, and the output will be available after delay 1. And the pace at which constructors are available in the inputs, it's the pace at which you will receive constructor in the output. For multiplication, you can see that depending on your implementation, so that's the most standard one, the one we would write naturally in a sequential model. The output is delayed by something that depends on the size of the first argument. And if you're a little bit clever, you can find another way to do multiplication, and you can make this output delay constant. But it only works for paces that are bigger than 2. So depending on what you want to do with them, you might want to choose one or the other. We obtain a theorem for parallel complexity that is very similar to the other one. It has the same shape. What has changed is that now we use schedule types, so they have to satisfy the new rules for the reduction rules have to satisfy this delay consumption property. You need to make sure that the potential attributed to delayed computation is decreasing. It's bigger than the potential without delay plus the delay itself. And the way to combine potentials has changed. It's not a sum anymore, it's a maximum. That's the kind of library annotations you need to deal with, natural numbers. And as you can see, you have some timing information, as we have seen, plus some total running time and total space needed to run the computation for this node. Now I will say a couple of things about higher order. So for now, we have some restrictions. So we only deal with weak reductions. That corresponds to no reduction under lambdas in normal lambda calculus. And to lift this restriction, we would have to find a way to keep track of function sizes. What's the size of the body of functions? So it can probably be done, but for now, we don't do it. We only use sequential reduction because this subtyping property was only available for algebraic types. For functional types, it doesn't work as well. We will need some more clever way to annotate possible delays between inputs and outputs of the functions. So all in all, it's just very similar to what normal implementation of functional programming language do. That's the kind of types we obtain for higher order functions, such as map and fold. So you have the simple case where you access some function many times, and to type it, you just need to annotate the number of calls here. So map will only make n calls to the functional argument, but all users are the resources for each call are the same. In the case of fold, it's more complicated because the output of the first call will be used as an input for the next call, and the resources you need for each call may vary. Thanks. And in this case, you need to have some non-homogeneous multi-set of types, which you can represent with this kind of sugar in the types. So I've only shown very simple examples for now. With this approach, this methodology, it's possible to actually type the example I've shown in the introduction slide, so merge sort. Merge sort relies on auxiliary functions, split and merge. It's possible to type them, appropriately annotate the types with sizes. In particular, just the fact that everything types checked correctly proves that merge sorts makes only f of n calls to the comparison function, and f of n is exactly this thing. It's approximately n log n. So you have, just by type checking, you have a proof that merge sorts can only make n log n calls to the comparison function. And on top of that, you can add complexity bounds, that's time. It's defined according to f again. And that's the amount of space you need to perform merge sort. So you can check, on the next slide I have the reduction rules. You can check that if you sum all the potentials here, they will be bigger than the sum of the potentials here with the appropriate hypothesis that was found in the theorem. So when you are used to read graphs, it's just like normal lambda terms. It's quite natural to follow the flow of resources that have been added to the types. So I will conclude. So what I've presented is some kind of methodology for checkable complexity specification. So I've presented it in the interaction net framework because everything is concise because there's only one main construction, it's a node, but it's not fundamental. I suppose it could be, the same IDs could be adapted to function on your favorite language. It works with different resources. So I've mentioned space and time. We are also able to do space-time, which is space occupation as a function of time. You have not only the full amount of space you need, but you have the amount of space you need depending on the running time. It works for sequential and parallel models. It is type-based, so using size types and newly introduced schedule types. It's potential-based, which means that you can do amortized analysis easily. It is general and not restricted to, for example, polynomial classes. We've seen logarithms in the typing of M sort. You can also certify exponential bounds, for example, if you fold multiplication. And we could extend this to higher order for now with some restrictions. So the future work would be to lift those restrictions. And one important thing would also be partial automation of type inference, because I've shown some coefficients, and they were computed by hand. But in practice, you want them to depend on the kind of hardware you have. And you would really like to, at least for the coefficient, have a procedure that computes them automatically. Thank you for your attention.
Question? So you say that you're essentially computing the complexity of merge sort by type checking, but moving from the complexity of the comparison operation to the complexity of the full merge sort, you essentially apply the master theorem, right?
Yes, so I've skipped some details to answer this. This does not include the costs of calling the function, but the typing scheme here should be enough to, is enough to know what will be the cost of all the calls. Because in this case, you only need to know how many calls there will be, because you use the resources in an homogeneous way. So just the number of calls should be enough to know. The number of calls and the resources inside A here should be enough to know what will be the cost of each call to the function. In more complicated cases, like fold, which is here, you have here a summary of how the calls to the functional argument will be made. And it's enough to later, or when you add to your sum of potential the potentials associated to the body of your function, it's enough to take care of those costs.
I have two questions. So the first one is, can you deal with resources that become available, as for instance with space, when you deallocate something? So that there was a first one, and the second one is, so does this presentation with these like interaction nets has an advantage compared to working directly on lambda terms or something like that?
So for the first question, resources that become available, like dynamically changing?
No, I mean like with space, for instance, when you have like deallocations, so where you gain resources instead of paying for it.
So in interaction nets, all garbage collection or allocation is done explicitly. So I'm not sure how to speak about this kind of resources. Your second question was, I'm sorry.
If it has an advantage to use them.
So the main advantage is that the theorem, you've seen the statement of the whole theorem in 3 lines. If you had to do the same for lambda calculus, for example, you would have like 15 inference rules that share all the same property, but here it's concise.
Any more questions? One last one. For the higher order case, are you able to describe the class of programs for which your analyses can be applied to? For example, like forms of recursion.
Some kind of completeness theorem. No, I know I'm able to type, things like map and fold. If you give me the potentials of the function that you plug here, I'm able to compute the costs of folding this operation. It's some examples that work, but I don't have any, so I cannot claim I can deal with everything.
What about forms of recursion?
Forms?
Are you able to say what forms of recursion fits into your framework or can be typed?
No, that's a good question, but I don't know exactly.
Let's thank the speaker again. So organizers, any announcement?